This video will be about particle equilibrium. So what is particle equilibrium? Particle equilibrium is described as the summation of forces on a particle equating to zero. So this is a particle. So let's say we have forces F1, F2, and F3 on this particle. We know that vectors can be added, and this equation states that the summation of all of these forces will equal to zero. So let's do a quick example. Let's say F1 is equal to 3i, F2 is equal to 4j, and F3 is unknown. So we know that the summation of forces in the x direction is equal to zero, and the summation of forces in the y direction is equal to zero, as well as the summation of vector forces being equal to zero. So as you notice, this is a scalar and this is a scalar, whereas this is a vector, because when we say the summation of forces in the x direction, the direction is already defined. So what we do is, let's say this is the F1 as a vector, but F1x is 3. Let's also put some units on this. So this is newtons, and that's 3 newtons. Let's look at F1y. That is going to be equal to 0j, so that's just 0, because F1 only has an x component denoted with this I right here. And then graphically, we can see that as well, where the vector is horizontal. So again, we define two methods of solving this problem. The scalar statement, and the vector statement, So let's go ahead and solve this with the vector statement first and the scalar statement second. The vector statement says that the summation of all vector forces, I'm just going to quickly redraw the diagram really quick because we want to see it visually. And then let's also define our axes. So this is our y-axis, this is our x-axis. Something that will be very important for this course is whenever you draw a free body diagram like this, at this point, many of us know that this is called a free body diagram. Whenever you draw that free body diagram, make sure that you definitely have your axes defined. Otherwise, on problem sets, you will have a lot of issues because you'll get points taken off. Make sure you define your axes. So let's look at the summation of our forces. We have F1 plus F2 plus F3 equal to 0, because the problem states that this is in equilibrium. I forgot to mention that, but this system is in equilibrium. Without this assumption, we could not find F3 based on the given information. If we know that this system is in equilibrium, that's the only way that we could find F3. Otherwise, we would not be able to. So let's solve this expression. We know F1 is 3i and F2 is 4j based on how we defined it here. And now let's add F3 and equate it to 0. Doing some algebra on this, we see that F3 is equal to negative 3i minus 4j. So this is one method of solving this very simple particle equilibrium example. So this is the vector method. And let's solve the same problem using the scalar method. So in the scalar method, what we're doing is we know what F1 is as a vector. And we basically take this vector and split it into its x and y components. So let's do that here. So for F1, we had F1x is 3 newtons. Oh, one important thing that I forgot to add. This guy needs some units. That's very important. Don't forget units. And moving on, f1 y is 0 because this vector only has an x component. So let's look at f2. f2x is 0 because f2 is a vector that only has a y component, and f2y is 4 newtons, as we can see, positive 4 newtons. So for the scalar statement, as we can see, what is happening is we are solving two expressions. We're solving the x direction and the y direction separately. So let's do that. We have fx is x direction 3, and this is 0, plus f3x, because we have the unknown, this is our unknown, equal to 0. And then let's solve this. f3x is negative 3 newtons. Now let's do the same for the y direction, and then that's going to be 4 plus f3y equal to 0, which is f3y equal to negative 4 newtons. And again, we have the same answer as the previous method. And if you want to grab this and turn this into a vector, that's very easy. So we just do f3 is its x component, negative 3i, minus 4j newtons, which is the same answer as we got here. And this method is the scalar method. And this example was for two-dimensional situations. For three-dimensional situations, we also have a very similar approach where the vector method stays the same because we know the addition property of Cartesian vectors. You just add them up together, even if there's a k direction as well. You just add them up. And for the scalar method, you would have to add the fx direction, the fy direction, and the fz direction. So the same method works for 3 dimensions as well. Moving on, one of those elements is cables / strings. So these elements are only in tension. They can only be in tension. So let's say we have a cable, quick drawing, that looks like this. It cannot be compressed because if it is, then it would look like this. So it would be called a slack cable or a slack string. So compression does not work. And then let's consider some rigid bodies such as beams. Beams can be in tension and compression. So there can be a force like that or like this. And the third element is springs. Springs can both be in compression and tension. Compression and tension. Now let's consider some other types of elements that we will be interacting with, but this time it won't be tension compression. Let's talk about elements with contact forces. Contact forces. And these are basically rigid bodies that are in contact with a surface. There can be friction present. Or it can be a frictionless surface. Another type of element that we will be considering is pulley. Pulleys are circular bodies that are often home to cables that are in tension, and they are secured to whatever they are attached to with a pin at the center of the pulley. So let's consider this pulley where we have the circle and we have two symmetrical cables that are in tension and the magnitude of the tension are the same, then what will be the reaction force at this pin right here? So let's think about this. I'm going to draw this again, this time with a hole, and then we will be considering the pin as a different body because the pulley is an element of its own and the pin is the supporting structure for that pulley. So let's say this is our pin, and then we have a pulley with a hole inside of it, and we're basically putting this pulley on this pin. So if we do that, let's say these marks show where the hole is. And basically this pulley that is in tension because of these two strings, it's in tension, is in equilibrium because this pin is supporting it. It's preventing when something's pulling down on this pulley, but the reason why the pulley remains stationary is because the pin, this pin right here, is applying a reaction force on the pulley. So basically, the free body diagram of this pin, so this is the pin, and I'm drawing a free body diagram, is subject to a force brought upon the pulley by these two tension forces. So let's precisely call this 2Ty. So we have 2Ty, this force that is acting on the pulley, and thereby, since the pulley is making contact with this pin right here, this force is applying on the pin right here, this pin right here. And as a result of this contact force, the pin is providing an equal and opposite reaction, assuming that this is in equilibrium. And right now, that's what we're considering. This pulley is in equilibrium. And that's why there is an equal and opposite reaction by the pin that is the same magnitude of that. And let's call this reaction force R. So basically, this is the free body diagram of the pin. So now I want to draw a free body diagram of the pulley, And for the pulley, our free body diagram would look like we have, but before I do that, I want to define the axes for this really quick, for this free body diagram. And I also want to define axes for the pulley free body diagram. So when we look at the pulley, we see that there's a cable applying tension in this direction and another cable applying the tension in this direction. So then in order for this pulley to be in equilibrium, because let's say assume pulley is in equilibrium. So basically it's not moving, the pulley isn't turning, it's not going up and down, it's in equilibrium. It's stationary. And this pin is acting on the pulley as such. So this is the reaction force of the pin. To make it more clear, I'm going to grab this vector and move it here. And now we have a nice free body diagram. So I've done this much explanation on this example, so let's turn it into a problem. So our problem will be T is 10 newtons and angle theta, where I will define theta as such, and angle theta is equal to, let's say, 60 degrees. Find the reaction force at the pin. So let's see. We have the pulley. Let's solve it with this free body diagram. We're given an angle, and I'm going to draw this angle right here. This is theta. We're given an angle, and we're given magnitude. So let's recall how we solve these particle problems. We do summation of forces in the x direction, and we do summation of forces in the y direction. So the x direction, when we look at the free body diagram, it doesn't really interest us because for the x direction, the only components that exist is the tx in this direction and the tx in that direction. And this is pointless to solve because the summation of the forces in the x direction is just giving us tx minus tx, which is obviously equal to 0. So this is basically pointless. So let's consider the y direction. Summation of forces in the y direction tells us vector r minus ty minus ty equals 0. And notice the signs here. The signs are very important. We're doing that because r is pointed in the positive y direction, and both t's are pointed in the negative y direction. So we want the negative sign in front of the y component of vector t. So let's do some quick algebra on this. R is negative 2ty, and that's why I also labeled this guy 2ty, because I already sort of knew, but we solved it, and that's what we have. So now, all that's preventing us from finding r is that we don't know what ty is. So how do we find ty? It's very simple. We've done it many times before. That's t times cosine theta, so cosine 60, which will give us 5 newtons. So ty is 5 newtons. So let's see what r equals. R is negative 2 times 5 newtons, which is negative 10 newtons. So we have solved the problem. Though I did realize that I made a silly mistake here, as I got the ty's on the other side of the equation. I forgot to get the negative sign off, so let's fix that really quick. And we have r equals 10 newtons. And that is our answer. And we're going to be looking at another pulley example really quick, but I will not solve this one. So let's say we have a circle, and then a force with angle theta, and another force where this one is at a different angle, specifically parallel to the y-axis. So this is parallel. And the reaction force at this pin will actually be a two-dimensional vector rather than a scalar quantity, because there will be a ry component and an rx component. And let's call these vectors t1 and t2. The reaction force at this pin will have both a y and an x component, because as opposed to the previous example here, so in this previous example, the t's were symmetrical across the y-axis, right? And this means that their horizontal forces, tx and tx, both of the tx's, canceled each other out. Therefore, at the pin, a horizontal reaction force was not necessary. However, here, the T2 is parallel to the y-axis. So there is no pre-existing force that points in the x direction that counteracts the x component of T1. So nothing is counteracting T1x except for Rx. Therefore, Rx is necessary, which means that the reaction force has an Rx and a Ry component. So to wrap it up, let's talk about our strategy for solving particle equilibriums. So step 1 is we always start with an FBD. Very, very important. Without a free body diagram, you're probably not going to solve many of the mechanics questions. The second step is to define your coordinate system. So this is basically the difference between using a coordinate system that looks like this or using a tilted coordinate system. So looks like this. I will now draw 2 diagrams where we can distinguish which coordinate system is better. So for number 1, we want to use the tilted coordinate system, and we want to tilt this coordinate system by an angle of theta, which equals 30. This is because this is tilted by an angle of 30. And for system 2, we want a coordinate system that looks like this, where x is parallel to the horizontal and y is parallel to the vertical, because these forces They're 90 degrees between them. It's very convenient to use a non-tilted coordinate system. And finally, the number 3 for our strategy is to apply the following equations. Summation of forces equals 0 for directions x, y, and z. And that's all for particle equilibrium, and have a nice day.